Hello, my dear student. Assalamu alaikum. This is Dr. Aisha Nazuk here, and this is one of my lecture series on the course Applied Econometrics. Today we are going to discuss regression with panel data, and I'm using chapter 10 of Stock and Watson book that you can easily download from the internet. I'll take this opportunity also to introduce the Genesis library. Let me type the Genesis library URL here. So this is an interface of Genesis library. Okay. So this is the URL gen.lib.rus.ec. So from this library you can download any book. So for example, if I want to download econometrics and I type Watson and I click on search. So you see, Introduction to Econometrics. This is the Stock and Watson book for the 2008 edition, and you can have different years editions here. So the lecture series that I'm using here is referring to Stock and Watson book 2015 year. But I'm sure if you can not download this particular edition, you can equally or efficiently use any other edition of the book. Of course, there will be some change in the chapter number. Okay, so regression with panel data. Up till now, we have been, analyzing the aspects of cross-sectional data or simple time series data. And we've also studied the concepts of multiple regression. You all know that multiple regression is a powerful tool for controlling the effect of variables on which we have data. Of course, if you want to run any model and if you want to include any variable in your model, you need to have data on that. That is a foremost and a very, you could say, easily understandable requirement. But what if the data are not available for some of the variables, right? So they cannot be included in regression. And the OLS, or the ordinary least square estimator of the regression coefficient, could have omitted variable bias. So what are we saying here? That there are some factors that you believe are very important and they can efficiently explain the variation in your dependent variable. Like in other or easy words, that they are a good determinants of the dependent variable, but you don't have data on them, and that's why you don't include them in the regression. But by doing so, you are inducing a problem in your regression, which we often call the omitted variable bias. So how to go about in such scenario? So we have a magic wand stick, I will use the word, because this is so frequently used, um, and people have been making best use of panel data, which requires collection of data over time, collection of data on same cross sections over time. So, by the way, if you are unaware of the basic terminologies like what is a cross-sectional data or a time series, a panel or a pooled data, I strongly request or advise that you brush up over these basic skills, like you can get yourself acquainted with these terms like the panel data, time series data, and cross-sectional data. Otherwise, it will be quite difficult to understand the ideas explained in this lecture. Okay, so by making use of the panel data, we can control the omitted variable bias, right? So if you can recall, what is the omitted variable bias? That is the bias induced due to not including some important variables in your regression model, right? Okay, so what is a panel data? The data in which each observation, unit or entity is observed at two or more time periods is called the panel data, right? For example, if a very basic example is that we have like two students and we keep on recording their semester CGPA for, let's say, 8 semesters. So we have two, you could say, entities, right? By entity or unit, I mean the cross-sectional or the basic data generating units. For example, in this example, students are the entities. And since we are recording their CGPA or the cumulative GPA for 8 semester, so the time period in this scenario is 8, right? Okay, so this is how I will also give you an imagery based illustration of the panel data in the coming few slides, so that sometime you always say like a picture is loud worth 1,000 words, so we can explain the concept of panel data through a picture soon. Okay, so by studying changes in the dependent variable over time, it is possible to control or circumvent the omitted variable bias, especially when the omitted variable that differ across entities but are constant over time. So don't get carried away by some fancy terminologies. What I'm saying here in basic word is that uh, if the omitted variables are supposed or expected to be different across cross section, like in the last example of students, if there are some variables that may differ across students, but they are constant over time. For example, the IQ level varies from student to student. But in general, if we observe the IQ of a single student over time, it is expected to remain constant. So that is what we are saying, that panel data is very useful to control for the bias of omitted variables in such scenarios. Okay, by the way, today's lecture or this video covers quite, you could say, widespread, or maybe that choice of word is not correct, quite, you could say, demanding concepts. So if you are watching this video, it's highly advised that maybe after like 10 minutes or 15 minutes, you can take a short break. You can, if you're constantly sitting in front of a computer screen, it's highly advised just take few steps, maybe sip a glass of water, relax, and then start watching the video again, so that you are understanding the concepts and you are not stressed out while watching the lecture. Okay, so the notation for panel data. Let the ordered pair xit yit, where I varies 1 to n, that is, I represent the variation in cross section. For example, in the last example that we were discussing about two students, I would have varied from 1 to 2 because we had only two students. But in general, we can say I can vary from 1 till n. That depends how many cross sections or how many entities are we studying. Then T is the index for time that varies from 1, 2, 3, so on till capital T. For example, in the last example, we were analyzing the CGPA of two students for 8 semester. So 8 would have varied, T would have varied from 1 to 3 and so on till 8, because we were keeping data for 8 semester. So in general, I is a index for cross section, T is the index for time, right? So yit is the ith value of the dependent variable for the tth time period, right? Like yit is one single value, which is for ith cross section. For example, it may be for second student for the tth time period. For example, it may be the marks of the second student for the 7th semester, right? So that would be y27, right? So in general, we have YIT, right? XIT is similarly the same notation for independent variable, right? Okay. So panel data is also called longitudinal data, and this pair of x and y, it refers to the pair of dependent and independent variables for n different cross sections observed at t different time periods. Now let's discuss the two type of data, panel data we can have. Balanced panel. A balanced panel has all its observation That is, the variable are observed for each entity and each time period. In simple words, in balanced panel, we don't have any missing values, right? All the data is available. But in unbalanced panel, what happens? We have some missing data, right? We can have one missing value or we can have two missing value. So that is called a unbalanced panel. So let us depict the balanced and unbalanced panels with the help of a simple example. Let's say we have four different students and we represent those students by the rotation S1, S2, S3 and S4. So these are four different students. And let's say we are recording their CGPA, that is cumulative GPA, at the end of each year, right? This time we are observing the CGPA by the end of each year, academic year. So Y1 represent year 1, Y2 represent year 2, and so on. So these values that are written here in the corner, like 6, 4, 3, etc. Let me explain what these values are. I have written here for your convenience. Um, so these values, these small values in the triangle sort of a figure, these represent the average weekly study hours. Like an average, the student is studying, for example, 6 hours per week. The same student S1 started studying 4 hours per week in year 2 and so on. The values here in the rectangle 2.14, 2.36, etc. These represent their cumulative GPA, right? So this is an example of balanced panel because you could see that no data is missing. Now we have an example of unbalanced panel. Pardon that this heading is not being written correctly. This is example of unbalanced panel, right? You can make correction in your notes. This is an example of unbalanced panel. So in unbalanced panel, what happens that we may have some missing value. Just assume that the student 1 gets withdrawn from the university, maybe due to some disciplinary action. So we don't have his CGPA values for the year 3 and year 4. So this is a unbalanced panel because some of the values are missing. Okay, so why are we discussing the two different types of panels? Actually, the econometric handling that we discuss pertains to balanced panel, but especially in Stata is very efficient in handling unbalanced panel as well. So whatever we discuss in the later part of this lecture is relevant both for balanced as well as unbalanced panels. So you need to know the difference between balanced and unbalanced panel, that apart from this lecture, if you are studying any test for panel data, make sure that its assumptions are relevant for unbalanced panel as well if you have unbalanced panel. So what I mean to say is, if you have an unbalanced panel, make sure that the statistical test that you are using is relevant or efficient for use in unbalanced panels as well. Okay, so next we have panel data with two time periods, also called the before and after comparisons. Okay, when the data for each entity, for example, if each entity is a state, right? And if we have data for each entity for two time periods, then it is possible to compare the values of the dependent variable in the second period to the values in the first period. Actually, why we are discussing specifically panel data with two time periods first is that without making use of specific panel data analysis econometric procedures, if we have only two time periods, we can simply use a alternate form of OLS to estimate such models, and we will be able to control the omitted variable bias as well. Okay, so for example, we want to predict the changes in the dependent variable, that is before and after comparison, and it holds constants the unobserved variable from cross section to cross section. What is it's being said here, that even if we have omitted variable bias that is expected to differ from cross section to cross section, but it remained constant within each cross section. If you are unable to quickly comprehend this, just refer back to that example of students where we were discussing their CGPA. So if the unobserved variable is, for example, IQ of the students, then it differs from student to student, but it does not changes over time for one particular student, right? Like over time variation are so minimal, even if there are, that we assume that there are no overtime changes in IQ for a particular student. Okay, so let Gi be a variable that determines the cross-section specific variable that does not change over time. For example, in the last example, IQ is called Zi. And since we have assumed that IQ is fixed over time for a particular student, so we have omitted the index T in here. That's why we have written this variable only as Zi, because it is expected to stay constant over time, right? So we have another example to understand this whole notion of holding some unobserved factors constant over time. So, for example, if we are analyzing the determinants of traffic accidents in different states of the United States, USA, then ZI may be the local cultural attitude toward drinking and driving, right? Because the cultural attitude, you know that even if they change over time, the changes are so slow that we can consider them to be constant for two different time periods. For example, if the time periods are 1982 and 1988, we can say that the cultural attitudes about drinking and driving cannot change so quickly between these two time periods. So if we want to analyze the determinants of fatal accidents, we can regress fatality rate on the beer tax. Like we are saying that how fatal the accident is also depends upon what is the beer tax in that state. Because you know that one of the determinants of an accident being fatal is that if the driver was drunk. That's why we are saying, analyzing the impact of beer tax on fatality rate. So let's say we have the variable BTIT is the beer tax for the ith state in the th time period, and over here we are considering only two time periods, so t varies from 1 till 2, right? Now the population regression function relating Zi, that is the state-specific cultural attitude toward drinking and driving. Then, what is the regression function? Fertility rate, right? And we have used the notation FRIT. So fertility rate is a function of beer tax and some state-specific unobserved factor. For example, we said that the local cultural attitude towards drinking and driving. So how to get rid of this Zi from this equation? Because this is an unobserved factor. We don't have data on it. Okay. So what we can do is we can, run two different regression, one using the 1982 data and the other using the 1988 data, and then we can take the difference. Actually, these two equations, we won't be actually running those regression. We will be only looking at these regression equations so that we can understand the actual regression that we will be running. If we take the difference between these two equations, we get this simple OLS equation. That is, we will be taking differences in fertility rate from the two time period, right? And we will store that in one column. And we will also be taking difference of the beer tax for the two time period, storing it in another column, and simply regress those differences on each other, right? This this whole thing will be stored in one column. This whole thing, beer tax, will be stored in another column. And you may be wondering, what is this? This is nothing but the regression error. If you simply run the OLS using these differences on this one, you will get some errors that will be stored here. So if you have only two time periods, it's very easy to analyze. Just take the differences of the dependent and the independent variable across the two time period, use the OLS. But it's not necessary that all the time you have only two time periods. You can have data on more than two time periods. So the first type of panel data model that we use for more than or two or more than time periods is the fixed effect regression that has some specific assumption attached to it that we will be studying with the passage of time. So fixed effect regression or FER is a method for controlling for omitted variables in panel data. As we introduced earlier, the same concept that the omitted variable vary across cross section, but they are not expected to change over time. So unlike before and after comparison, the fixed effect regression or the FER can be used for two or more time periods. That is, you can use FER for two time periods as well as for more than two time periods. So the fixed effect regression has n different intercepts. Currently, you may not be able to quickly understand this. So give yourself a little bit of discount, and in the coming few minutes, you will understand what is this notion of different intercept. So it has n different intercept, one for each cross section, right? So note that the different intercept can be represented by a set of dummy variables. That is actually what's happening, that you have different cross sections. For example, if you have in the last example 4 students, so you can have one dummy for student number 2, the other one for student number 3, and then student number 4. And I haven't introduced dummy for student number 1 because that student will become the base category. As you know that the number of dummy variables that we introduce in a model is always one less than the number of categories to avoid dummy variable trap. So if you don't know dummy variable trap, kindly read about it so that you avoid those type of errors while introducing the dummy variables. Okay, so what am I saying is that the fixed effect regression is actually equivalent to introducing dummy variables for cross sections, right? Because the whole idea is relying or banking upon the fact that the variations are across cross sections. That is why we are introducing dummies only for cross sections, right? But fixed effect regression can be, run directly without using these dummies. But the reason why I'm relating with these dummies is because if you have the basic idea of dummy variable, whenever you introduce a simple dummy variable in a model, you are actually changing the intercept. That is why we have said that the fixed effect regression has n different intercepts. So the fixed effect regression model, suppose we have data on fatality rate of accident and we regress upon the observed regressor beer tax and the time invariant, that is something that does not changes over time, and the time invariant factor, state specific perception or culture about drinking and driving, ZR. Then we have this type of a regression, fatality rate as a function of beer tax and unobserved variable ZR. So what is the purpose of this regression is to estimate the effect of beer tax on fatality rate while we control for the impact of state specific characteristic Z, that is culture about drinking and driving. It could be anything, but here we have discussed this particular variable. Given that GI varies across states, yet it is constant over time, so we may express one as B1, beta 1 BTIT, that is this term, beta 1 BTIT. Then this beta naught and beta 2 ZI is clubbed together and we call it alpha I, right? This alpha I contains this beta naught and beta 2 ZI. And because these are constant over time, that is why we have clubbed these two terms. And then you have UIT. So this is the reason we said that the fixed effect regression has n different intercepts, because this alpha I, this will be alpha 1 for the first cross section, alpha 2 for the second cross section, and so on. So these alpha are intercepts, right? So we have, if the number of cross section is n, we have n different intercepts in the fixed effect regression. So as I said that we can also understand n different intercept by using dichotomous dummy variables. For example, instead of expressing the fixed effect regression the way just we did, let's introduce an alternate exposition of the same model, beta naught plus beta 1 vertex plus now we have a dummy variable for the second cross section, for the third, and so on. And as I said, the first cross section will become the reference category to avoid the dummy variable trap. Now this is equation 2, and if you look at equation number 1 just for a purpose of comparison. So this equation 1 is simply this one, where we have expressed fertility rate in the form of these beta naught, beta 1, beta 2. Whereas what we have done that instead of this beta 2 zi, we have introduced these gamma related dummies, right? So these are actually two different ways of stating the same model. So we can say if we compare equation 1 and 2 that alpha I is beta naught plus gamma I. If you are unable to understand right now, just write both these equations on a paper and then compare, right? This is your equation number 1 and this is your equation number 2. So just write these on a paper and then you will easily understand alpha I is beta naught plus gamma I. So for example, alpha 2 is the intercept for the second cross section. Alpha 2 is also equal to beta naught plus beta 2 zi. So what we are saying is that if we put this particular value, we compare this alpha 2 here with equation number 1. So you can see, just a second, pardon for that. So alpha 2 will be beta naught plus beta 2 zi. Since dummy 2 is equal to 1 for the second state, so the intercept is beta naught plus gamma 2. So what I'm saying is that for the second state, from this equation, what will be the intercept? Beta naught plus, we will put d2 is equal to 1, so beta naught plus gamma 2. So this is the intercept. So that's how we can say that alpha I is equal to beta naught plus gamma. By the way, if you're not a student of mathematics and you're watching this video, you're studying applied econometrics from a social science perspective, maybe this particular part or this particular display right here on your screen is not that relevant, so you may not worry if you don't understand this. But for those students, those who have the background of mathematics and they're enrolled in a degree which demands for high use of mathematics in econometrics, they are expected to understand this. If you don't, I will shortly share my email ID and I will also mention my email ID in the comment section so you can always get in touch with me. Okay. The FER or the fixed effect regression model for multiple regressors. So unlike the previous form where we have only one independent variable, which was the vertex. So but in general your y variable could be anything. So we have written the general form yit as a function of x1 it, x2 it, and so on, and plus alpha I, which are the n different intercepts for the cross section, plus UIT. So you can also express the same thing using the dummy variable as we just did, that we introduce one dummy for each cross section while we kept one dummy or one cross section as the base group. Okay, so regression software use special function to quickly estimate fixed effect regression. So the dummy variable based exposition of the fixed effect regression, it's a theoretical concept just to build your concept about the background working. But the statistical software, they directly run the fixed effect regression without using these dummy variables. So now we discuss running fixed effect regression in Stata. So let's refer to a particular data set that for my students I have uploaded on their learning management system portal, that is the LMS portal, or the Microsoft team page for the course. For the general viewers, they can get this data by writing an email to me, which will be displayed shortly, my email address. Okay. So what I have done is I've opened Stata and I've opened a data file which is known as fertility rate hypothetical data. So this particular data, let me tell you, this is an hypothetical data. So that is why I haven't mentioned any source for this data. So you see there are 4 different columns here. CS is the cross-section number. So cross-section 111 means these are observations from, for example, you can say first state of USA. These are 222 are observation from the second state of USA, and so on. Then you can see the variation in time from 2002 to 2005 for each state. Then we have data on fertility rate and we have data on beer tax. And you can see that the observation number 28 fertility rate data is missing. So this is unbalanced panel, right? Okay. So before using Stata command to run the fixed effect regression, we have to introduce which particular variable is about cross section and which is about time. Like, of course, while we enter, we know that, like I just discussed here, that this first column contains cross section and this here contains time period. But to Stata, we have to tell. And how do we tell? We use this command xt set. For example, if the column name about cross section is cs and about time period is year, so we write this command xt set cs year. So let me write here xt set cs year, right? So write this command xt set cs year. So this type of an output is here, that the panel variable is cs, time variable is year, and it's telling me the variation from 2000 to 2005. Delta is 1 unit because the time period or the year they vary by 1 unit. That is, after 2000 we have 2001, right? And CS is unbalanced, as we just told that there is a missing value in the data. As I just told you that in row number 28 we have a missing value. So Stata has detected that and declared that this panel is unbalanced. Okay. So coming back, this is the Stata command for fixed effect regression, xtrec, and then we have the dependent variable, that is fertility rate dependent upon beer tax, right? So this should be fr and this should be bt. So as you can see the data file here, fr is the fertility rate and bt is the beer tax. So this is a sort of a writing error. This is fr, that is fertility rate, and this bt, that is beer tax. So you have xtreg, then you have the dependent variable followed by the independent variable and comma fe, so that Stata would know that we are opting for fixed effect regression. So using the Stata file fertility rate data, as I just said that I've uploaded that for my student on the relevant portals, and general viewer can write me an email. Here is my email ID, right? I will also write the email ID in the comment section, so you can get the Stata file from me so that you can relate to these video. So an important assumption of fixed effect regression is that the time invariant cross-sectional characteristics are not correlated with the other cross-sectional characteristics, right? That is, what was time invariant? In the fertility rate example, we treated the culture about drinking and driving to be time invariant cross-sectional characteristics. So we are saying that those characteristics, they are not correlated with the other cross-sectional characteristic. For example, the other cross-sectional characteristic that we included in the regression was beer tax. So there is no correlation between beer tax and the culture about drinking and driving. That is one of the assumptions. Then the cross-sectional error term and the cross-sectional intercept should not be mutually correlated. So what does that mean? That the error term or the regression error term in the cross-section and the cross-sectional intercept. What is cross-section intercept? It is actually average effect of omitted variable that may influence the cross sections or that may be important in the cross section. So what we are saying is that the omitted variable are uncorrelated with the error terms, right? If the error terms are correlated, then fixed effect regression is not suitable and we have to opt for other type of model. For example, one you would study later is the random effects regression. So if we suspect autocorrelation and heteroscedasticity, if you, the viewers are not acquainted about these terms, please brush up your econometric skills about autocorrelation and heteroscedasticity. And if you want me to post another video on these basics, please do write in the comment section. So if we suspect autocorrelation and heteroscedasticity in the data, then we may use the Stata command xtreg followed by the dependent variable, then the independent variable, comma, fixed effect, and then we can use this VCE cluster cross-section variable. So this VCE cluster cross-section variable, for example, we had the cross-section in the CS column. So we will write VCE cluster CS. What will this do is that the formulas that they are calculated in the background, they will be equally valid even if we have the problem of autocorrelation and heteroscedasticity in the data. So if you have the problem of auto and hetero in your data, it is advised to use this command xtreg and this one, right? So for example, if I want to run this command here, xtreg, then you have fertility rate, comma, and space beer tax, and then FE, and you write VCE, and then you write cluster CS, right? The command that I just shared here on the paper. So that's what I have written here. So option, just a minute, let me find a solution to why this. Okay, so let me write the command that I was by mistake. There was a little bit mistake when I typed earlier. So xtreg, then the dependent variable fertility rate, and then the independent variable beer tax, then comma FE for the fixed effect, and then you write VCE, and then you write cluster, and then CS. Right, so now these regression results, they are, you can use even if you have the problem of autocorrelation and heteroscedasticity in your data. Okay, so we were discussing the case for when we have the problem of autocorrelation and heteroscedasticity in the data, then we can use this type of command that we just ran in the Stata software. Okay, so referring to the fertility rate data, the regression line that we just estimated, right, is this. Let me see the output. So you can see the constant is 0.100 and the beer tax is minus 0.07. So these are the coefficients, and these coefficients are being used if you have the problem of autocorrelation and heteroscedasticity in the data. And for example, if you don't have any such problem, then you can simply use the ordinary command, which is xtreg fertility rate beer tax, comma FE. So now you have these coefficients, right? So apparently the coefficients are same, but you can see the standard error column, this is different. So these standard errors, specifically those who want to use this confidence interval part, or they want to do hypothesis testing, then they should be worried about the problem of autocorrelation and heteroscedasticity. Okay, so this is the regression line that we just copied here on the page. So fertility rate is this. So what we are going to interpret is the simple OLS based interpretation, that is, if we increase the beer tax by 1 unit, then the fertility rate is expected to decrease by 0.0734 units. And whether this beer tax is a significant determinant of fertility rate or not, you can see its p-value. So over here, this p-value is not less than or equal to 0.05, so we will say it's not significant. But if you have this variable as significant, then you can interpret. So here, for the time being, I am assuming that this is significant. That is, this value is less than or equal to 0.05. That is why I am interpreting, right? Okay. So this is the interpretation of the significance value. So then we have the f-test p-value here in the Stata output as well. If you see, we have this f-test and the p-value is given here, prob greater than f. So what is the interpretation of this p-value? If the f-test p-value is less than or equal to 0.05, then you can conclude that the regressor explains the dependent variable efficiently, right? Now coming to the assumption of no cross-sectional dependence. Actually, when we are running the fixed effect regression, one of the prime assumption is that the cross-section, they are mutually independent. That is, for example, if we were discussing that students and CGP example, then student 1 is independent of student 2. Their marks are independent. So in some cases, the cross sections are not independent. So then we cannot directly use fixed effect regression. So if we have to test whether the cross section are dependent or not, we can run a command xtcsd, but we have to find it, right? It's not readily installed in Stata. So if we type find it xtcsd, right? I type find it xtcsd, right? Find it xtcsd. So what will happen? Stata will connect to the server, and depending upon your internet speed, you will see different links from where you can install this command. For example, if I click on this link, and then I can click here to install. And currently I'm not clicking because I've already installed, but you can click here, and then the xtcsd command will be installed in Stata. Right now you can type the Stata command for Pesseran test, which is used both for unbalanced and balanced panels. So if you type xtcsd comma Pesseran, and if that the probability value is less than or equal to 0.05, then you can say that there is a problem of cross-sectional dependence, right? So what we have to type xtcsd comma Pesseran, right? xtcsd comma Pesseran. Pesseran. This is the name of the researcher, the Pesseran, who proposed this test. So, oh, I type CDS, so I have to type again xtcsd comma Pesseran, right? xtcsd. I have to check a little bit why this error is being displayed here. Yes. So I'm sorry, I was doing a little spelling error. That's why the command was not being run. So just for the sake of repetition or revision, what we do, let's run the fixed effect regression again. xtreg, fertility rate, beer tax, fe, right? And then we want to apply the Pesseran test. So this is the command, right? I was doing a little bit a spelling error earlier on, so that's why it's not being run. So xtcsd comma Pesseran. So this is what you have to type, and you will get this p-value, or the p-value equal to 0.9610. So what is the interpretation? If this probability is less than or equal to 0.05, which is not the case in our data, only if this probability is less than or equal to 0.05, then you say that there is a problem of cross-sectional dependence. And if you have a problem of cross-sectional dependence and still you want to run the regression, then you use another command. You find it xtscc. This is a specific type of standard error that can be used even in the problem of cross-sectional dependence. So type find it xtscc and you will be diverted towards some sources or the URL from where you can install this command, install this one, and then you type xtscc dependent variable followed by the independent variable, and then your estimates will be reliable even if you have the problem of cross-sectional dependence. So this is all about the discussion relevant to today as concept, that is the fixed effect regressions and the panel data. And I advise that you watch this video more than once to efficiently understand the topic that we have covered in today's video. And if you want me to post also a short video about a specific aspect in this lecture, do let me know through your comments or write me an email that I've already shared my email ID. So best of luck, and we stop the today's lecture.